Right, in this video we're going to cover structure of amines, physical properties, and the basicity of amines. Also some factors that are affecting basicity. So we'll be going through sections 19-3 to 19-6 in your textbook. Alright, so if we look at amines, an amine is sp3 hybridized, and it can undergo what's commonly referred to as an inversion. This normally isn't a big deal unless you have a chiral center right where the nitrogen is. For instance, I have a nitrogen with 4 different substituents here, which would make it chiral, and the lone pair of electrons would have the lowest priority, and so we would call this S ethyl methyl amine. And once again, this is an sp3 hybridized center, so the lone pair is sp3 hybridized. Then if it undergoes an inversion, it goes from an S to an R, and so it's impossible to isolate one or the other because it keeps inverting so fast. So this is R ethyl methyl amine. And then sort of the transition state between the two inversions is an sp2 hybridized structure where the lone pair sits in a unhybridized p orbital. And once again, this is sp2 hybridized, so I'm trying to draw it so it shows that it's trigonal planar in terms of its shape. Didn't do the best job, but that's okay. So there are other chiral amines too that you actually can isolate, and we'll look at some of those examples. For instance, you can have an amine where you have an asymmetric carbon as the chiral center and the nitrogen is just one of the substituents, and those we can isolate. A good example is S-butane 2-amine. It took me a minute to draw that. And once again, this I'll put a star on the carbon where it's a chiral center. So if we draw the R buta2-amine, it would look like this. Okay, and so we can isolate both enantiomers. A quaternary ammonia group also can be chiral. For instance, let's the nitrogen is the chiral center. I'm going to just write pH for a phenyl group, and then we have an ethyl group, both in the plane of the paper. And then coming out of us, we'll have out of the page, we'll have a methyl group, and then going into the page we'll have an isopropyl group. And so this is an R, but there's also a corresponding anion that we don't really care about, so we won't draw it. But you can also have an S, and because we don't have that lone pair of electrons we don't have an inversion taking place. So there's my isopropyl group going into the page, methyl group coming out, and another ethyl group staying in the page. And this is an S. Okay, so quaternary ammonia groups can have a chiral center. Another example is when the nitrogen atom is in a really small ring. Flip that on the next page. Oops, got my pages mixed up here. And yeah, I'm just going to show this to you. It's a little bit easier. So I've already drawn it here just for the sake of time, but here is a nitrogen in a three-membered ring, and the chiral center is the nitrogen, right? Because notice we put two methyl groups over here, so it's not symmetrical. And that way that nitrogen is chiral, and it's an R. The lone pair has, once again, the lowest priority, so it will be facing away from you when you assign the priority to determine if it's R or S. But it can't undergo an inversion because of the ring. The ring keeps it stable. Of course, here's the corresponding S. Okay, so let's talk about physical properties of amines a little bit. Amines have hydrogen bonding, but it's not hydrogen bonding like you would have in water or low molecular weight alcohols, because nitrogen doesn't have as high of electronegativity as oxygen. In fact, oxygen has an electronegativity of about 3.5, where nitrogen is 3.0. And the oxygen is the second highest element in the periodic table when it comes to electronegativity. So you do have the hydrogen bonding, but it's not like you would as in a water molecule or an alcohol. In general, the primary and secondary amines have a lower boiling points than the alcohols, and they're also higher than ethers too. Mainly that's due to, like, the alcohols have stronger hydrogen bonding, and that's just the primary and the secondary amines. They have the lower boiling points. Mainly also because if you have an alkyl group, that donates electrons to the nitrogen. So that decreases the electron density on the nitrogen. One important thing here is part 3, though, is that alcohols and primary amines, if you have more than 5 carbons on them, they won't be soluble in water. I can't tell you how many times I've used that in the lab where I'm trying to figure out, okay, is this thing going to be soluble in solution or not? Well, if you have the tail end of a carbon chain, if it has less than 5, then they're going to be soluble. Most amines also, they smell like rotten fish, so you know instantly when you're working with them. In fact, the smell will penetrate your clothes many times, and you can smell all day if you're working with an amine. So amines can act like a base, and they can act like a nucleophile. If we think about what happens with a base, right? A Bronsted-Lowry base is something that wants to reach out and grab a proton. So if we throw an amine in water, let's assume it's a soluble amine, it'll grab that proton off the water molecule and it'll form an OH and a quaternary ammonium group. We consider these to be weak bases, even though everything's relative, right? If you compare an amine to hydrochloric acid or sulfuric acid, it's weak. Right? However, if you compare a primary amine to a tertiary amine, then maybe it's strong. Okay? But there's a value of Kb, an equilibrium constant, which hopefully you remember from freshman chemistry. But the Kb represents products over reactants, right? The concentration in moles per liter. This is concentration of the OH ion and the concentration of the quaternary ammonia group divided by the concentration of the amine. And water is left out of the equation, but this is a unitless number. And the bigger the Kb is, the stronger the base, because the higher the concentration of the OH ion. Okay. If we move forward a little bit, amines can behave like nucleophiles too, because you have that lone pair. I didn't draw the products in here, but you have a lone pair of electrons on the nitrogen, right? They can donate to an electrophile, which in this case is the a methyl group with an iodine attached to it. The iodine is a leaving group. Remember, this is a polar bond, so that carbon is a good electrophile and the nitrogen is a good nucleophile, and the nitrogen donates its electrons, so it's behaving as a Lewis base, and the methyl halide is behaving as a Lewis acid. And you guys know the rest of the story. This is an SN2 reaction, which I won't, once again, I didn't draw the products in there. But the Kb, if we go back to acids and bases, the bigger the Kb, the stronger the base. Okay. Also, you can have a pKb too, which equals minus the log of the Kb. So the smaller the Kb, the stronger the base. Also, the bigger the pKa, the stronger the base. Because remember, there's a relationship between pKa and pKb, right? 14 equals the pKa plus the pKb, which is also some freshman chemistry that hopefully it's coming back to you a little bit. So let's think about what factors will affect how basic an amine is. If we look at the alkyl groups at ammonia versus a methylamine, one alkyl group will help to stabilize the positive charge on the nitrogen, right? Because if you have, here's a methyl group, we'll just say an R group, and it reacting with water to make that quaternary ammonia group, which has got a positive charge. I need more space here to write. Okay, having that R group will help donate electrons to the nitrogen, and it will help to stabilize that positive charge. But if you start getting more than one alkyl group, then you have solvent effects, right? Because you get a sort of a greasy outer layer, and that means it's less soluble in a polar solvent like water, and that's going to favor going back the other direction towards the reactant side. So one alkyl group makes it a stronger base. More than two alkyl groups tend to make it a weaker base. So keep that in mind. Another thing we also have to be concerned with are resonance effects on basicity. You'll notice that here we have a compound which is aromatic, because the lone pair of electrons on the nitrogen are in a p orbital. So we have 2, 4, 6 pi electrons, and that follows Huckel's rule. It's also a flat molecule, and so that means this is aromatic, it's resonance stabilized. But if we protonate those electrons that are on a p orbital, right, we form our quaternary ammonia group, but we only have 4 pi electrons now instead of 6 pi electrons, and now it's not aromatic. So that's less stable, and so that means it's going to favor it going to the equilibrium will favor the reactant side rather than the product side. Therefore, it's a weak base. Notice the Kb is 1 times 10 to the minus 15. Not very basic. But if we look at pyrimidine, those electrons sitting over here, if we protonate it, those electrons are sitting in a sp2 hybridized orbital. It's not a p orbital. Okay, so if we protonate it, we still have 6 pi electrons sitting over here, and we still have 6 pi electrons, so we didn't lose the aromatic character of that molecule. And so pyridine will be a much stronger base than the first molecule we talked about, the pyrrole, because once again we're not losing the aromatic character of the molecule. Notice the Kb is 1 times 10 to the minus 9 instead of 1 times 10 to the minus 17. So they're both weak bases, but the pyrimidine is a stronger base than the pyrrole. Okay. Let's talk about hybridization effects too. So the more S character you have, the harder it is for you to go out and grab a proton. So notice with pyrimidine, the lone pair of electrons is sp2 hybridized. We have a Kb of 1.9 times 10 to the minus 9, right? So we don't lose the aromatic character, but if we compare it to a 6-membered ring with an sp3 hybridized molecule, right, then if this grabs a proton from the water, get a positive charge, but this is much more hybridized, less S character than what you have on the pyridine. And notice the Kb is 1.32 times 10 to the minus 3. So to kind of summarize, when it comes to basicity, it's the number of alkyl groups, its resonance effects, and then we also have the amount of S character of the lone pair of electrons on the nitrogen. That affects how strong of a base it is. Okay, so that concludes factors affecting basicity. Now on the next video, we'll get into some spectroscopy and reactions with amines.